The viscosity of a liquid depends on the strength of its intermolecular forces. Glycerol has relatively strong intermolecular forces and is rather viscous. Its resistance to flow is high. Ethanol, by contrast, has weaker intermolecular forces. It flows easily and has low viscosity.
Viscosity is referred to as the resistance of liquids to flow. And viscosity is actually a pretty hardcore subject and stuff, but one of the many factors that influences the viscosity of a liquid is the intermolecular forces. And in this video, we looked at ethanol in the lower left and glycerol, which is in kind of the middle right. And if you look at the hydrogens connected to oxygens, and oxygens are red, you can see that ethanol has one OH and glycerol has three OHs. Well, the more OHs you have, the stronger the interaction will be for the molecules to other molecules. And glycerol, a triol, has three OHs. And so one reason why glycerol is slower to pour is that the molecules really hold on to each other, and it's harder to get it to flow. Ethanol, on the other hand, with one OH would be flowing more like water, all right? Water and ethanol both have just individual OHs, so it's not quite the same. Viscosity is a lot of things. It's more than just the intermolecular forces, but one of the major forces in viscosity discussions is how much they stick to each other. Intermolecular forces will help out. Another thing about liquids is that, like we saw earlier, the surface of the liquid is where a lot of the action occurs. And the reason for that is liquid molecules on the surface have a net inward force. So the little liquid molecule there circled on the top, it's going to be pulled to the left and the right and down, but there's nothing over above it. The water molecule, they're kind of down towards the bottom of the picture, has water literally all the way around it, top, bottom, left, right, forward, backwards. So it's just having basically a net force. And this inward force is really interesting. It leads to this phenomena called surface tension. And surface tension is just an energy that's required to break the surface of the liquid. And some substances have strong surface tensions, and some substances have weak surface tensions.
A paperclip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paperclip sinks.
Surface tension is really important for the biological world. Insects can actually float on water, and that's kind of their way, and birds come down and eat them or whatever. Things in biology I don't understand. But anyway, this is only possible because, again, the surface of the liquid is a little different. There's actually a little bit of force. And if you have small things like a paperclip or a bug for that matter, they can actually float. However, you saw in the video that they added a little bit of soap to the water. That broke the surface tension. And then the paperclip ended up sinking. If you have like an oil spill in the wild, the oil is like the soap. It breaks a lot of the surface tension. The poor little insects then can't float and they drown and stuff like that. So there's a lot of implications for surface tension, and understanding how it works makes you a better chemist. So which of the following substances do you think will have the strongest surface tension? Okay. And again, strongest surface tension is going to be related to the intermolecular forces. So let's think about these in terms of intermolecular forces. And if you look at those compounds, all right, the first compound has an SH. This is called a thiol. Sulfur, like oxygen, is going to have two lone pairs on it if you draw the Lewis structure out. So A would be a compound which has dipole-dipole forces. It's polar, so it's going to be pretty strong. The second compound has oxygen in the middle of two carbons. Oxygen, like the sulfur before it, if you draw it out, it's going to have two lone pairs, polar, all right, but not hydrogen bonded because the oxygen is not directly reconnected to the hydrogen. So B would also be a dipole-dipole interaction. The third one, though, has that magical OH, and OH is one of the possibilities you can have for hydrogen bonding. The OH can connect to another OH and stuff and make that happen. And if you quickly look at D and E, they're a lot like A and B. They either have sulfur or they have oxygen not connected to a hydrogen. So I would predict that answer C is the right answer, and it is. As intermolecular forces go up, you have stronger surface tension. The soap is basically a non-polar substance. It doesn't have hardly any surface tension. So stronger intermolecular forces, stronger surface tension. Cool. Capillary action is another function of these intermolecular forces. And there's a thing we have to talk about here. Cohesive forces are interactions between like particles, and adhesive forces are interactions between unlike particles. And believe it or not, this can have a big effect when it comes to glass. Now, this is two pictures here of a glass, if you will, like a tube, all right, or a capillary, sometimes they're called. And we have on the left-hand side a water molecule, which is probably like you can even think about it like wine. All right, wine has basically like a water in it, of course, with other things. On the right-hand side, you have mercury. All right, and mercury is metallic, which is another kind of a force. And so water is a lot like the forces in glass. All right, glass has an alternating silicon-oxygen linkage. The reds are oxygens and the grays are silicon, and most glass is this kind of way. Silicon-oxygen makes polar bonds, and water is polar, hydrogen-bonded polar even. So when you put water in glass, the water actually climbs the side of the glass molecule. So notice at the top there, the water actually makes like kind of a lower dip. All right, and this is called a concave meniscus. Concave means it makes like a little U kind of in the water, and that's because the water is actually climbing the surface of the glass. So glass is usually polar, water is polar, it's going to grab on. These are the cohesive forces, if you will. On the other hand, in mercury, all right, you have then a convex meniscus. Mercury is a different kind of bonding from the polar glass, and they don't get along really well. All right. So in these cases, then you're going to end up with a convex kind of a little bulge. You can see that the mercury is trying to get away, if you will, from the glass because they're different kinds of forces. It's a different kind of thing. So polar substances in glass create concave meniscuses. And if you have anything that's not polar, i.e. metal or non-polar things, convex. It's going to make a little bit of a bulge.
When a piece of paper is dipped in water, the water moves up the paper by capillary action. The attraction of the water to the surface of the solid paper allows the water to rise against the force of gravity.
Paper is essentially a series of carbons with OHs on them, more or less. That's a very simple version of what paper is. But anyway, if you place paper in water, the water also likes, if you will, the paper, and it will climb up. And this is another result of this capillary action. So if you've ever had a newspaper and, I spilled my coffee on it or something like that, well, it goes all over. It doesn't just go where it poured. It actually like spreads out, and that's the capillary action. The cellulose is kind of like water, so there's similar kinds of bonds, so they get along, if you will, really well. So it spreads out. This is another effect of capillary action. The next topic we're going to look at is how to actually calculate the energy required to turn one substance into another. And we've done this a little bit in the past, but we're going to look at it in a little bit more detail here. So we're going to look at heat transfer with phase changes. And there's all different kinds of possibilities. But before we go into the details, and before we feel too bad about the poor little rabbit there in the video, remember that anytime you have a solid and you turn it into a liquid, or you have a liquid that you turn into a gas, that's going to be endothermic. It's going to take energy to make that transformation possible. On the opposite side, though, gases going to liquids and liquids going to solids, you actually get the energy back out again, and those are actually exothermic processes. So down here in this kind of picture, you can see there's a big solid, a liquid, and a gas, and there's also the different terms used for these processes. So as an example of that, vaporization, which we talked about earlier, is liquid going to gas, and that's going to take energy. It's going to be endothermic. On the other hand, condensation is the opposite process, going from a gas to a liquid. That's going to be exothermic. But there's other terms here as well. Some of them are familiar, some of them may not. Solids going to liquids, the process is referred to as melting, and liquids going to solids, of course, that's freezing. But there's also solids going to gas. That's the sublimation. We saw the iodine crystals turned into a gas. And then technically, deposition is the term used for going from a gas back to a solid. So if you turn the iodine crystals back into a solid iodine, that would be a deposition. Those are the terms used for the different phase changes. And in Chem 221, we looked at some of these. In Chem 221, I referred them to as a heat of something times a mass of something, and those are the energies to make the transitions of phases possible. We're also going to throw back into this mix the Q equals MC delta T kind of stuff that we did in Chem 221. And Q equals MC delta T is really useful when you have a temperature change, but no change in phase. So as if you had nothing else to do with your life, if any of this is looking weird, go back and look at the chapter 5 stuff of Chem 221. And you can look at it if you go to the website, which is mhchem.org/221. You can check out all the chapter 5 stuff. We're going to reuse some of that stuff in this discussion. If you're going to have a change of state, so liquid to vapor or gas, you're going to need the heat of something. And a heat of vaporization is the term that's an energy required to turn a liquid into a gas. And all these heat of vaporizations are positive numbers. They're all endothermic. So if you have, for water, example, the heat of vaporization is 40.7 kilojoules per mole. The temperature in parentheses is the normal boiling point that would occur. And you can see sulfur dioxide and xenon. But notice here how the value of delta H of vaporization gets larger as the intermolecular forces get larger. So xenon, which has just induced dipole, has the smallest heat of vaporization, and water, which is stronger than dipole SO2, has the largest heat of vaporization in this list. A heat of fusion is the term required if you take a solid and you turn it into a liquid. And again, that's another endothermic process. You can have a heat of fusion for water, SO2, xenon. The trend is the same. Weaker intermolecular forces generally have lower heats of fusion and larger ones are larger. Pretty cool. Now, the temperature is constant during a phase change, and we'll talk about that here in a little bit. But you might be curious, like, how the heck do they get these heat of vaporization values? Well, two scientists named Clausius and Clapeyron came together, and they figured out this kind of weird-looking equation right here. And this is actually how they can calculate things like heat of fusion, all right, or heat of vaporization or heat of any of these things. If you plot the natural log of the vapor pressure versus 1 over the Kelvin temperature, you end up with a straight line. And that little graph right there shows the straight line that happens when you plot on the Clausius-Clapeyron equation. First of all, natural log is different than base 10 log. So on a calculator, usually there's an LN button and an LOG button. You want to make sure you use the natural log, which is LN, and not the base 10 log, which is LOG. All right. And the vapor pressure values are usually in millimeters of mercury. So you just take the natural log of your vapor pressure, put those on the y-axis. Now, all of those vapor pressures are recorded at a temperature. Usually, initially, it's in Celsius. You would turn it into a Kelvin temperature, all right, by adding 273.15 to it, and then take the inverse, which means go 1 over the Kelvin temperature. And if you do that, you get a nice straight line. The slope of the line is really important to chemists. All right, this is a negative slope, and we'll talk about this a little bit more in one of the labs coming up, but the slope equals negative delta H divided by R. So what they're doing is they're plotting 1 over the temperature, so slope equals negative delta H vap over R. And R, this is the energy R that we talked about briefly in the gas law expression. You can actually solve for the delta H vap value. Delta H vap will equal the negative slope times R. It comes out to be a value in joules per Kelvin. Linear regression is the math technique that's used to get the best value for slope. And we're going to have a lab about that here pretty soon, the linear regression in solids lab. But you can also do a cheesy version of Clausius-Clapeyron if you only have 2 values using this equation right here. The P1 and P2 are the vapor pressures, and the T2 and T1 are the Kelvin temperatures that you'd use. And R is the constant, so you can solve for delta H vap. Notice it's natural log P1 over P2, and the temperatures are 1 over T2 minus 1 over T1. Be careful of that. To get rid of the negative sign in the above equation, they flip the pressures around or the temperatures around. Anyway, this is maybe TMI, more information than you need, but this is literally how they get the delta H vaporization values, and it's pretty cool how they figured it out. It's not something that I do every day, that's for sure, but it is something that all of us can do if the need arises. This is an example that we looked at a little bit in Chem 221, and we're going to come back here and do this again. And this is basically a type of a curve you would see for either heating up water or cooling water, depending on which way you go. First thing you need to see is that there is a constant line right here, and that represents the part where ice is melting. So on the left-hand side, you would have solid ice. On the right-hand side, at the end of that straight line, you would have liquid water. So melting is going from a solid to a liquid, and notice that the temperature is constant. Temperature is the y-axis here. In Chem 221, we saw how the mass of something times the heat of something, there was no temperature associated with it. That was just the energy to turn, for example, the solid into a liquid. So there's no temperature changes when you melt the ice. The next part, if we're going from melting to turning it into steam, is we would heat the water. And if you look here, going from this point to this point, there is a change in temperature, i.e. the y-axis value is changing. So this is heating the water, but no change in phase. You have just liquid water going from the bottom circle to the top circle, all right? And this is where we use MC delta T. M is the mass of water, C would be the heat capacity of liquid water, 4.184, and delta T, final temperature minus initial temperature. So for water, that would be 100 minus 0. 100 is where we ended there at the top circle. 0 is where we started there after we first melted the ice. The next part there is a big line that goes straight across, and that's where you're turning the liquid water on the left to steam on the right. I'm going to try and use like a square here to show the difference there. The temperature is also constant, just like when we melted the ice to liquid water. When you turn liquid water to steam, you're not changing the temperature, still 100 degrees, but it does take energy to break apart those liquid molecules and turn them into steam. So that's the evaporation process. So let's put all of this in kind of a practical example. Let's take 500 grams of ice at 0 degrees Celsius and heat it to steam, which is gaseous water, at 100 degrees. And we're going to need some constants for this. The heat of fusion for ice, which is the energy required to melt the solid, all right, 333 joules per gram. The specific heat of liquid water, which we talked about in Chem 221, and a number I'd like you to know / memorize, 4.184 joules per gram Kelvin. And finally, the heat of vaporization is the energy required to turn liquid water into gaseous water, 2260 joules per gram. So in this problem, we're going to take solid ice and heat it up to turn it into a liquid. And it's going to take 333 joules per gram of ice to turn the solid into a liquid. Then we're going to heat the liquid from 0 to 100 degrees. That's going to be a Q equals mc delta T problem. And finally, with our liquid at 100 degrees, we're going to turn it into gas, steam. It's going to take 2260 joules per gram of liquid water to turn it into steam. So this is going to be a 3-part problem. The first problem, we're going to use the 333 joules per gram, and that's just to melt the ice. The second part of the problem, is going to be one of the Q equals mc delta T things. We're changing the temperature. We'll use that 4.184 number to figure out the energy. And then finally, step 3 will turn the liquid water into the gas. That'll be with the 2260 number. So 3 parts to this problem, and we'll add up the 3 answers to get the overall answer to this problem. Let's go through the math. First, we're going to melt the ice, and that's where that 333 joules per gram number comes in. We have 500 grams of ice. We're going to turn it into a liquid. 333 joules is required to turn 1 gram of ice into liquid water. Do the math, 3 sig figs, 1.67 times 10 to the 5th joules to turn the 500 grams of ice to liquid water. Now we're going to raise the water up to 100 degrees Celsius. Remember, we want to turn the ice to gas, and the only way we can do that is if we heat the water to 100 degrees. So this is a Q equals mc delta T problem. 4.184 is the heat capacity of liquid water. Still have 500 grams of water, and the delta T final minus initial can be Celsius or Kelvin, doesn't matter. So it's 100 degrees for delta T either way. 3 sig figs, 2.09 times 10 to the 5th joules. Notice that the energy required to heat the water about equal to the energy required to melt the ice. Kind of interesting. The final part here, we're going to take our liquid water at 100 degrees and turn it into a gas at 100 degrees. And that's where that 2260 number comes in. We have 500 grams of water, 2260 joules to turn 1 gram of liquid water into a gas, 3 sig figs, 1.13 times 10 to the 6 joules. Notice how much more energy it took to convert the liquid to a gas than it did to turn solid into a liquid or to heat the liquid water from 0 to 100. We're breaking the intermolecular forces there in step 3, and it's almost a full magnitude of energy higher than the other 2 processes. So the final answer then to turn the ice to vapor is going to be the sum of steps 1, 2, and 3 all put together. So if you add up 1.67 times 10 to the 5th plus 2.09 times 10 to the 5th plus 1.13 times 10 to the 6th, you get 1.51 times 10 to the 6th. We're adding things together. We have to cut this number off at the larger doubtful digit, which is right there. So that's why it's 1.51 times 10 to the 6th. If you want to divide by 1,000, turn it into kilojoules, 1,510 kilojoules to convert your ice at 0 degrees Celsius to steam at 100 degrees Celsius. And again, the interesting part, at least for this part of the problem, is that it sure took a lot more energy to turn the liquid water to a gas than it did the other 2 steps. A phase diagram is just a graph, if you will, that shows the three states of matter. And all phase diagrams look something like a Y, all right? And the Y, which I've kind of drawn right there, the solid is always on the left, the liquid is in the middle of the Y, and the gas is on the right side. So you can see that on that graph axes, you have pressure on the left, temperature on the right, and there's some really interesting kind of parts here. But why this is neat for scientists is that it can tell you things like what temperature a solid will go to a liquid, or how can I get my solid compound to turn directly into a gas. So there's lots of little kind of neat things about these phase diagrams, and we'll see some examples of them coming up. All of the phase diagrams look something like this one right here. This is the phase diagram for water. You can look in your textbook for an even better version stuff, but this one will work fine as well. The lines on there, the Y part are the lines. They show all the conditions at temperature and pressure where an equilibrium exists between the different phases. So these lines, the parts of the Y, will show you like when things boil and when things melt and sublime and all this kind of stuff. And you can also see what phase your substance will be in if you know the temperature and pressure. So these can be super useful for scientists and engineers and a whole bunch of different kinds of fields. This is a little animation that shows the solid, all right? Solids, again, are very rigidly held together, but there is a little bit of movement. It's not totally dead. The only time you wouldn't have any interactions would be at 0 Kelvin. So solids, again, pretty tight. Now, if you heat up the solid a little bit, i.e. go left to right on the graph, you get to the point where you have both the solid and the liquid. And this is where the process of melting occurs. So the purple dots on the right would be like the liquid version, and the more blue dots on the left would be the solid version. And at the melting point, you have both solid and liquid at the same time. If you keep heating up the substance, eventually all this stuff will turn liquid. We'll look at that in a little bit. But for right now, let's look at this graph down here. This is a phase diagram for oxygen, O2, all right? And one thing that's really interesting is in the picture we saw earlier for water, all right? The solid-liquid interface, which is this part right here, for water had a negative slope. And in this picture here, the solid-liquid line has a positive slope. Now remember, if the line goes up and to the left, it's negative, or in the liquid oxygen one with the graph right there, the line is going up and to the right, that would be a positive slope. If you have a positive slope, the solid phase is more dense than the liquid phase. And like we talked about earlier, if you have something more dense, it goes to the bottom, less dense on top. So what this means for oxygen here is with a positive slope, solid oxygen would sink in liquid oxygen. On the other hand, if you go back to the beginning of this question, which I probably should have started about, I get kind of excited here, water has a negative slope. It increases up and to the left. And if that's the case, the liquid phase is more dense than the solid phase. So remember, ice cubes in water float, which is really wild. Most substances are going to be like oxygen, they sink. But because water has a negative slope for that solid liquid line, it means that the ice is actually less dense. So for oxygen, which is again the graph there on the right-hand side, because there's a solid slope right there, it's like the solid is pushing down on the liquid. That's what works for me. The solid phase is more dense than the liquid phase, and most substances have this kind of phenomena. Water is one of the few substances, not the only one, but one of the few, with a negative slope, and that just means that the liquid phase pushing down on the solid phase, liquid phase is more dense than the solid phase. So again, this is just reiterating how next time you put an ice cube in liquid water and it floats, that's kind of a cool thing in my world. Okay, moving back to the phase diagram, heating up from the solid-liquid interface, and there you can see the negative slope for water, by the way, you get to all liquid. And liquids are held together, but the intermolecular forces are not as tough as they were for the solids. So there's more like flexibility, if you will. But if you heat that up even more, you get to the next point, which is where the liquid and the gas are both in equilibrium with each other. So there you've got the kind of purplish dots on the top representing the liquid, and the gas, the red kind of crazy looking dots on the bottom, that would be the gas. So at first it is an equilibrium. You have both liquid and gas at the same time. The liquids don't just instantly turn into gas. All right, it's kind of a slow process. You have to go through all the different speeds of the molecules to get them right there. Kind of cool. And then finally, you heat it up enough and all of your liquid turns into a gas. Everything goes crazy. So that kind of stuff is pretty simple. We see it for water. You can take the solid ice and turn it into a gas by heating it up. That part's not too bad. But you can also have a solid go directly to a gas. And for water, this is weird. We'll talk about that in a little bit. Some substances do this naturally at room temperature and pressure. Carbon dioxide is a good example, which is dry ice. If you've ever been to like a Halloween party, and sometimes there's like punch and it's kind of got this gas stuff coming out. The gas is actually carbon dioxide. Carbon dioxide goes directly from solid CO2 to a gaseous CO2. So depending on the type of substance, you'll see this phenomena more easily than not. But even water will do this, which is really strange. There's another point which is absolutely worth talking about, and that's at the junction of the solid, liquid, and gas lines, like the middle part of the Y. And they call that the triple point. And at the triple point, all three phases are in equilibrium. And this is kind of like science fiction mind-blowing a little bit, maybe to some of you, but you literally will have the solid phase, the liquid phase, and the gas phase all at the same time. And you have to have very specific temperatures and pressures to make this happen. I'll show you in a video here in a little bit. But again, in theory, in addition to all substances in theory being able to go from solid to gas directly, you also have a triple point for all substances as well. So again, this is the phase diagram for oxygen, and I want you to give me the name of the point, which is where pressure is 2 millimeters of mercury. And this isn't the world's best graph, but the 2 millimeters mercury is right there. And the temperature is this 54.34 Kelvin. So i.e., what is the name of that point? And like we just talked about, when the three phases come together at the crux of the Y, that's the triple point. All right, so that would be where the triple point is for oxygen. And again, all substances in theory have a triple point somewhere if you get to the right pressure and temperature. These show the normal boiling points, the normal freezing points, and the triple point for water. Now, the normal boiling point is where the water boils under 1 atmosphere of pressure, 760 millimeters of mercury. And obviously, that's 100 degrees Celsius. In Fahrenheit, it would be 212, but don't say that around me. I hate that. Anyway, long story short. Freezing point, 0 degrees Celsius, 32 Fahrenheit, or 760 millimeters of mercury. So if you want to get to the triple point of water, and there's a picture of it right there, you have to be almost at 0 degrees Celsius, which isn't too hard. The pressure has to be pretty small, though, only 4.58 millimeters of mercury. So that's not a pressure that most of the time is seen for water, but if you get there, then you have that cool little picture right there. This is a video showing cyclohexane at the triple point. And cyclohexane, its triple point, occurs at 6.33 degrees Celsius and 40 torr. And a torr in a millimeter of mercury is the same thing, so about 40 millimeters of mercury. But you see there it's turning into a solid, but a liquid is forming, so that would be like a normal boiling. And now it's starting to turn into a gas, but now it's turning into a solid. Oops, there's some liquid bubbling out, and there's the gas. So you can see how it's going back and forth. There's the liquid. It really can't make up its mind. There's liquid going to gas. I can sit and watch this for a long time. It's so cool. Again, all substances should have a triple point. You may have to play with the temperature and the pressure a little bit to get there, but it is kind of cool. The last subject we're going to look at now in this particular chapter is we're going to look more at solids. And we haven't really talked about yet the ion-ion force or the metallic force and how they apply to the intermolecular forces. And that's what we're going to look at. So solids, when you think of all the solids in the whole world, there's basically two groups of solids. There's crystalline solids, which are just when you have the particles of the solid in highly ordered arrangement, so they are predictable in how they go together. But you also have what's called amorphous solids, and amorphous solids are more randomly placed together. The science and the understanding of amorphous solids is much more difficult and honestly not super well understood. So in Chem 222, we're only going to look at crystalline solids. So automatically, I'm pulling a lot of amorphous substances out, only looking at crystalline ones, but for the remainder of this time, that's going to be a good way to focus our energies. So we're only looking at crystalline solids. Crystalline solids are nice for this discussion because they're locked into what's called the crystal lattice, which means repeatable parts that are pretty close together. This is the classic positive-negative interactions we've seen since Chem 221. These have really strong intermolecular forces. The ion-ion force or metallic force, depending on what you have, we're going to consider those to be the strongest of the intermolecular forces by far, stronger than ion dipole, stronger than hydrogen bonding, stuff like that. These forces are so strong that it makes them very highly ordered. They're rigid and incompressible. So once you have them, you're not going to change their volume or something like that, like you could a gas. Crystal lattices exists as lattice points in an overall kind of larger parameter of where they are. So the little black circles and white circles right there represent, if you will, like cations and anions. And a scientist studying solids is really going to try and focus on where is the unit cell. And a unit cell is nothing more than the smallest repeating internal unit. And it has the characteristic of the solid itself. Now again, the amorphous solids, which we're not talking about, they don't have unit cells, so they're really tough to do, and that's why that's way beyond where we can do in Chem 222. But if you have a crystal lattice, you can find a unit cell, and there's different ways to interpret unit cells. The little green box is one type of unit cell down there where you have a black atom in the middle of the four white ones, but you could also have the kind of tan square one there where a white atom was inside and black atoms are on the outside. And I've drawn their 90-degree angles, but you can have them at all kinds of weird angles and stuff. The math part here gets kind of crazy. If you're a fan of geometry, you will love unit cells because unit cells are definitely dependent on angles and lengths and stuff like that. There's a whole bunch of different, what they call Brevais lattices. There's 7 main types of them, and there's the names for them, and there's a little picture there kind of on the left-hand side. Each one of these is worthy of a lecture unto itself, all right? And they're really cool. In my graduate school work, for example, I used to look at some examples of orthorhombic unit cells, and those were really cool. If you look there next to orthorhombic, you can see that all of the angles, alpha, beta, and gamma, they're all 90 degrees, but the lengths of the sides, A, B, and C, were all different. So there was some interesting geometry kind of going on there. In Chem 222, we're only going to look at the cubic, which is also known as isometric unit cells. And if you look down here at what makes an isometric or cubic cell, you have to have all the angles be 90 degrees, and all of the lengths of the sides, A, B, and C, they're all the same. So this is the simplest kind. It's probably, I would argue, maybe more common, but I don't know if that's fair or not actually to say. But what I do want to focus on here is that our discussion of solids is going to be very, very limited. We're only looking at crystalline solids, not the amorphous ones, which are hard to predict. And of the ones that we can predict, we're only looking at the cubic unit cells. We're not looking at the other kinds. In future chemistry courses, I encourage you to check out the other ones if they come up. But for right now, we're just looking at some simple examples to get an idea of how this stuff works. So in a cubic unit cell, which is only one of the 7 types, all right, all of the sides are equal lengths. So A, B, and C are all the same, and all of the angles are 90 degrees. If we wanted to find the volume of this cube, then A times B times C would equal the volume, and if A, B, and C are all the same, you could take the one side and cube it to find the volume, and that'll be helpful to us later on. Because our angles are all 90 degrees, we don't have to worry about sines, cosines, stuff like that, which is also kind of a bonus, to be honest. So again, we're picking essentially the simplest of these unit cells just to figure out how this stuff kind of works out. There are 3 types of cubic unit cells, and the first kind is called a simple cubic. So this is like a subset of the simple cubic of the cubic unit cell. And the simple cubic looks like that. All of those green dots there are like types of atoms. The second kind is called a body-centered cubic, and the third type is called a face-centered cubic. So we're going to abbreviate these SC, BCC, and FCC. Body-centered cubic has an atom inside the cell, all right? If you look at the inside of the simple cubic, there's no atom inside. But when it comes to the body-centered, there's like one right there. There's actually an atom inside the body of the cell, and that's why it's called body-centered cubic. Neither face-centered nor simple cubic has it. Now, face-centered cubic has an atom on each face of the cube. So I just circled the one on the top, if you will. There's also one here kind of facing us here, and there's one right here on the kind of left side. All 6 faces have an atom on their side, and that's why it's called the face-centered. So simple cubic is just the atoms in the corners, and that's it. Body-centered and face-centered have the atoms in the corner as well, but body-centered has an atom literally in the middle of the cell, and the face-centered cubic has an atom in each face of the cube, and that's what makes them different.
A simple cubic unit cell has one atom at each corner of a cube. The cells stack together to form a solid crystal, the overall shape of which has square edges. Each ion is shared by 8 different but connected cube cells. The arrangements of body-centered cubic and face-centered cubic unit cells are similar but more complex.
All 3 of the simple cubic unit cells had atoms in the corner of the cell. And those atoms in the corner, I want to point out that those atoms are actually shared by 8 different unit cells. So in the little animation right there, the yellow atom is not part of one particular cell. It's actually part of 8 cells. And so you can kind of see over here on the right that the little atom right there, it's like in this corner, this corner, this corner, this corner, etc., etc., etc. So when it comes to those atoms in the corners, we claim that they are 1/8 inside the cell, and that's going to be really important. Most of the atom is not in the cell. It's in the other 7 cubic unit cells right around it. This is the joy of the 3-dimensional cubic unit cell. So just realize right now that the atoms that are in the corners right there, those are only 1/8 inside the unit cell, and that's going to be important. So here's the simple cubic unit cell. And you can see in the animation on the right, it's like kind of like you're taking a chainsaw and you're cutting off the parts that aren't in the unit cell. And so each of those corner atoms, 1/8 is left in the cell, and the other 7/8 were essentially shaved. So when people talk about the number of atoms in a simple cubic cell, you have 8 atoms where there's 1/8 still left in the cube. So 8 times 1/8, simple cubic has 1 net atom. All right. So every time we talk about a simple cubic, you should think that there's 1 net atom. Technically, it's 8 times 1/8 atoms, but net is 1 net atom. Now, the other thing that we'll talk about more in lab is that it's going to be nice, because we're going to think about volumes and stuff, to think about the edge. Remember, in simple cubic, length, width, and height are all the same. The edge of a simple cubic cell equals 2 times the radius of the atom we're looking at. And that will be important coming up as well. So simple cubic unit cells have one net atom, and the edge equals 2 times the radius. This is the body-centered cubic. I'm going to shave off the parts of the atom which aren't in the unit cell, and when you do that, you're going to see that there still are the 8 times 1/8 atoms, those ones in the corner, but the body-centered also has an atom directly inside the body of the cell, and that stays there. So when it comes to numbers of atoms in the body-centered cubic cell, you've got 8 times 1/8, which is one net atom, plus the atom in the middle of the cell. So BCC unit cells have 2 net atoms per BCC cell. Now, I'm also going to put up here in the middle left here kind of what the edge to radius ratio is for these different unit cells. And in the solids and linear regression lab, if you're curious, we'll go over how those come around in more detail. But if you take 4 times the radius divided by the square root of 3, that's going to equal the edge of a BCC cell. And again, this comes from geometry, and you can read more about it in the lab. I won't talk about it here, but that's how you can go from the radius of one of these atoms to the edge of the cell. So 2 net atoms, edge equals 4r divided by square root of 3. That's the body-centered cubic unit cell, BCC. The third one is the face-centered cubic cell. These are also known as cubic close packing cells, and the difference between those is subtle and not something we need to go in right now. But anyway, like before, we're going to shave off the parts of the atoms which aren't in the unit cell and just look at the parts that are left over. This one in the main video takes a little bit. The lower left-hand corner shows what's going to happen. You can see how, again, you've got those 1/8 atoms, and there's 8 of them, but you also have the face atoms on this one. That's why it's called FCC, face-centered cells. And when you do that, the face atoms are still half in the cell. Half of it gets shaved off. There you can see the halves kind of coming off right now. So when it comes to the number of atoms, face-centered cubic, you still have the 8 times 1/8, which is one net atom, but now you have 6 faces with half of an atom per face. So 6 times 1/2 is 3, plus the 1/8 times 8, 1 atom, 4 net atoms per FCC cell. That's the amount of atoms that are still left once you shave it all off. So when it comes to face-centered cubic cells, 4 atoms per cell. And there's the relationship between the radius and the edge. 4 times the radius times divided by square root of 2 equals the edge. And you can read more about that in the solids lab if you're curious. But these will be important things coming up in what we're going to talk about. Here's the periodic table, and you can see the different types of metals especially that follow these examples. So the green one, polonium, the only one there in the lower right corner, is a simple cubic cell. It's got 1 net atom per cell, etc., etc. The body-centered cubics, the BCCs, basically all of group 1A plus a couple of transition metals, stuff like that, they will have 2 atoms per cell. Now, the other ones, definitely the orangish ones there, those are the face-centered cubics, FCC, with 4 atoms per cell. Hexagonal close packing is very close to face-centered. For us right now, we're going to consider that to be the same. It's not really. You'll do more with this in a future course if this is something you need to study. But for right now, just realize that a lot of the metals you can describe through either simple cubic, body-centered cubic, or some version of the face-centered cubic. X-ray crystallography is what scientists use to determine the type of cells, and they basically have an X-ray source that they place through some kind of crystal of the solid, and there's a scattering pattern, which is what that thing shows right there. And the scattering pattern can be interpreted to give these kind of analyses, and my hat's off to X-ray scientists and stuff. It's really, really cool. But that's how they figure all these things out. There's a lot of details that we're obviously omitting in this conversation, but I know someone is anxious to know what it is, and they do use X-ray crystallography to do it. X-ray crystallography is a pretty cool field. This is an example of a kind of problem you might see when it comes to this kind of stuff. And remember that what we're going to look at are just basically simple cubic, body-centered cubic, and face-centered cubic cells. So in this problem, we have aluminum has a density 2.699 grams per centimeter cubed, and the radius of an aluminum atom is 143 picometers. Let's verify that aluminum is face-centered cubic. Okay, so if aluminum is face-centered cubic, there's two things that'll tell us. One thing is that face-centered cubics have 4 atoms per cell. But the other thing is that if it's face-centered cubic, the edge of one of the cells is going to equal 4 times the radius divided by the square root of 2. So what we're going to do in this problem is we're going to start from the 4 times radius divided by square root of 2 to find edge, and then work our way over to 4 atoms per cell. We could have started with 4 atoms per cell and worked our way over to find the relationships on this side. But for this example, it's going to be easier to do it this way. So let's start with the edge equals 4 times the radius divided by square root of 2. The radius of the aluminum atom, 143 picometers. Now, a picometer is a metric prefix. Pico is 10 to the minus 12. So a picometer is 10 to the minus 12 meters. So a pico is something we'll run into once in a while. Another unit we'll run into in this section is an angstrom, and an angstrom is 10 to the minus 10 meters. We're going to run into some pretty small units. Angstrom is not technically a metric prefix, but it is used a lot in these, so just FYI. So you can see in this part of the problem, 4 times the radius, 143 picometers, divided by the square root of 2, 404 picometers. But because you can see the density is listed in grams per centimeter cubed, we better turn our picometer edge into a centimeter edge. So what you can do is take 404 picometers, multiply by 10 to the minus 12 meters per picometer to get rid of the picometers, and then you can divide by 10 to the minus 2 meters per 1 centimeter. 1 centimeter would be on top, 10 to the minus 2 on the bottom. If you combine those last two parts, you get 10 to the minus 10 centimeters per picometer, and either way is fine. But regardless, at the end of the day, the edge of our unit cell, 4.04 times 10 to the minus 8 centimeters. I do encourage you to go along with this example in your calculator so that you know how this works out and you know what's happening. Once you have the edge, because we're using these unit cells, length, width, and height are all the same. So the edge cubed will equal the volume. So if you take the 4.04 times 10 to the minus 8 centimeters and you cube it, you get a volume 6.62 times 10 to the minus 23rd centimeters cubed. And that is a really, really small volume. 1 milliliter is 1 centimeter cubed. I think a 12-ounce can of pop or beer or whatever would be 355 milliliters. This is 10 to the minus 23rd. So we're talking about super, super small volumes here because these are the little parts that make up the bulk aluminum. Pretty interesting. The density is in grams per centimeter cubed. So if we multiply that by the centimeters cubed, they cancel out, and you end up with how many grams are in a unit cell. And this is also a super small number. There's not a lot of mass, grams per unit cell, because again, the volume is also so small. You can also imagine that there's going to be a lot of unit cells in one of these chunks of aluminum. We're trying to get to the point where we are figuring out the number of atoms per unit cell. So one way to do this is you can figure out the mass of just one aluminum atom. So aluminum on the periodic table, 26.98 grams per mole. And a mole, by Avogadro's number, 6.022 times 10 to the 23rd atoms. So if you take 26.98 and divide it by Avogadro's, you get the grams per atom. And that number 4.480 times 10 to the minus 23rd. That's the mass per atom. So if you take that last number we calculated, 1.79 times 10 to the minus 22 grams per cell, and there's 4.480 times 10 to the minus 23rd grams per atom, this comes out to be 3.99 aluminum atoms per cell, and that's almost identical to 4. So we have just verified that aluminum is indeed face-centered cubic. It has 4 atoms per cell, very, very small. This is a kind of a strange way to do it, but you get the idea. We're going to do more with this kind of technique in the solids and linear regression lab, which we'll do here pretty soon. And the problem set will also have some of these problems. So if this stuff is looking a little weird, just hang on to that, and I think you'll see more examples. There's other kinds of crystalline solids beyond that. There's definitely the metallic ones we've seen. There is ionic, where you have positive, negatives kind of interacting. There's covalent networks, molecular forms, lots more to do with this stuff than we've looked at so far. So that's the end of chapter 10. Thank you for spending your time with me. We've looked at a lot of information in this section. I do recommend that you look at the study guide and the concept guide to get more ideas of places to study. The concept guide especially has a lot of examples to make sure you understand how this stuff works out. Following this is an important equation slide, which shows a lot of the equations you'll need to conquer this material. And then after that, there are some end of the chapter problems where the questions are given and then the answers follow it. Make sure you can do the questions and you're good. If you do have questions on any of this stuff, definitely reach out to me. Email is wonderful. I'll try to answer your question as soon as I can. You can also talk to the Learning Success Center / Avid Center at Mount Hood. They are there to help too. All right. Good luck with your studying and have a wonderful day.